All right. Good morning, everyone. We are recording now. Um, so, just want to make one or two quick announcements. Uh, we do have a TA. Shantini, I think, is in the call right now. Are you there?
Yes.
Okay. Thanks, Shantini. So, Shantini will be our TA for the course, right? And together, Shantini and I will be marking assignments and giving you feedback, etc. You may have noticed that in certain lectures or most lectures, I give you some DIY, do it yourself, and TIY, try it yourself problems. So at the end of the lecture, during the day or before the next lecture, Shantini will be compiling those and posting them on Piazza. Okay. Um, And what do I mean by DIY? DIY problems are generally a bit easy and they are supposed to help you in improving your understanding of the material that has been covered so far. DIY is generally slightly more difficult problems or problems that are related to the discussion we are going to have in the next or next to next lecture, right? So I want you to start thinking ahead about certain topics so that when we actually discuss it, you already have thought about the material. And DIY problems may also appear on your assignments sometimes. Okay, but the distinction is not super strict, but that is a vague distinction between the two. Are there any questions or concerns? You may discuss DIY or TIY problems or anything else except for assignment problems freely on Piazza. By freely, I mean you can have public discussions about it. And I actually strongly encourage using Piazza for discussing and resolving your doubts. Okay, good. All right. So, are there any questions or concerns pertaining to anything we have discussed so far, especially what we discussed in the last lecture? Right. So we discussed Hall's theorem for bipartite graphs, right? And I just want to spend a few more minutes today on talking about NP and CoNP and why do we care about these. So, just to recall, Hall's theorem says that you have a bipartite graph with cardinality of A equal to cardinality of B. Right? It says that the graph G has a perfect matching if and only if there does not exist any set S, subset of the vertex set vertices A, such that the neighborhood of the set is smaller than the set itself. Right? And such a set, if there is such a set, we call such a set a deficient set. Right? So Hall's theorem is saying that there is a perfect matching if and only if there is no deficient set. Okay, and this is good because if you look at the decision problem DP for perfect matchings for bipartite graphs, clearly this problem is already in NP because a perfect matching is a certificate, right? You can show a perfect matching to anyone and they cannot argue with you anymore that the graph does not have a perfect matching. And because of Hall's theorem, this problem is also on CoNP because if there is no perfect matching, then there is a deficient set and the deficient set is going to be your certificate. Okay. Just to remind you, NP and CoNP are not about algorithms. They are about the existence of certificates. These have nothing to do with algorithms. It's about certificates. Okay. So if you had some misconceptions regarding these things, this is a good time to get rid of those misconceptions. They're very common misconceptions. When I went for my master's, I also thought NP had something to do with algorithms. Okay, So why do we care so much about NP and CoNP? This course is not a course in complexity theory. In fact, this course, if anything, is more related to algorithms, because we are going to see algorithms, we are going to see polynomial time or efficient algorithms for combinatorial optimization problems using the theory of linear programming, right? And also using ideas from combinatorics itself. I mean graph theory mostly. Okay. So why should we care about these complexity classes? Well, let me try to give you an intuitive explanation. I won't give you a rigorous complexity theoretic explanation. Okay. So think about it this way. Supposing someone tells you that, hey, I have an algorithm that given any bipartite graph will find you a perfect matching if one exists, right? Well, you would like to believe this algorithm, right? And in particular, you would like to prove the correctness of algorithms, right? This is something you might have done in your DSA or DAA courses, algorithms related courses, right? So that is the short answer. You care about the correctness of algorithms because otherwise, why should you even believe that the algorithm works correctly, right? In particular, if I give you an algorithm, let's say I give you some efficient algorithm for this decision problem, that given a bipartite graph, it tells you whether the graph has a perfect matching or not. Okay? But well, when the algorithm terminates, it will give you some output, right? Yes, the graph has a perfect matching, or no, the graph does not have a perfect matching. But why should you believe the algorithm? If you look at any well-written, well-implemented algorithm, it also gives you a certificate. It doesn't just tell you yes or no, it also gives you a reason to believe the answer. In particular, if the graph has a perfect matching, it should give you a perfect matching for that algorithm, right? So for yes instances, the algorithm will give you a perfect matching. And when the graph does not have an algorithm, does not have a perfect matching, sorry, that's a no instance, the graph should give you some reason to believe that the answer is actually correct. The algorithm should give you some reason, right? And that reason is generally, in the case of this problem, is going to be a deficient set. So almost any algorithm for this particular problem, bipartite graph having a perfect matching or not, it will give you a deficient set if the graph does not have a perfect matching, right? And that is basically intuitively the reason why P is a subset of NP intersection CoNP. Okay, so I'm telling you this without going into Turing machines, deterministic, non-deterministic, all of this stuff, right? Basically, this is why the complexity class P, which is all the problems that are polytime solvable on a deterministic Turing machine, this complexity class is contained in NP intersection CoNP. So if you are trying to look for a polynomial time algorithm for some problem, it is a good idea to first think about certificates. If you can't find certificates, chances are your problem does not admit a polynomial time algorithm. Okay, so this is actually an important theorem in complexity theory, and I recommend that you take 6014, where this might be proved rigorously. In fact, a very important conjecture in complexity theory, while we are talking about these matters, is that P is a proper subset of NP intersection CoNP. In other words, there are problems in NP intersection CoNP that are not in P. So this stuff here is non-empty. And one such problem, if you are curious, it is beyond our course because it's not really a combinatorial optimization kind of problem. So it's integer factorization. Some of you may have seen this in your other courses, especially if you have ever taken a course on cryptography, you might have seen this. So that this problem belongs to NP intersection CoNP. However, it is not known to belong to P. That does not mean it does not belong to P. We just don't know. Right? If you can actually show that it does not belong to P, if you can prove that, you will have actually solved this very important conjecture in complexity theory. Okay? Are there any questions or concerns regarding this discussion? All right. So throughout this course, we are going to see lots of certificates. And the reason we care for certificates is precisely here. Okay? Good. So let's talk about a problem related to matchings that has been bothering at least one of you, Varun. So you might have also heard about the independent set problem. So remember, what is a matching? Matching is a set of edges such that no two share a vertex. So that no two edges share a vertex. Right? There is a very similar concept called an independent set. I'm going to call it a stable set, also known as independent set in various literature. But we might be using independent set for something else when we come to matroids. That is why I'm using stable set. So what is a stable set? Can you tell me, Varun?
So it should be that it should be the same. I mean, I'm confused. Not very clear with the definition. I feel it should be the same as matching, that no two edges that I choose have a common
No, no,
vertex.
no. So a stable set, I'll give you a hint. A stable set is a set of vertices. Okay. So now do you want to, but it's similar to matchings. So your intuition is not off. The difference is that a stable set is something about vertices and not about edges.
So if I choose any two vertices from that stable set, there is no edge between them.
Good, exactly. So it looks very similar, right? So it is a set of vertices. When I say set, I mean a subset of the edge set, right? Here I am in a subset of the vertices such that no two vertices share an edge in some sense, right? No two vertices have an edge joining them. Yeah? So it looks very similar. I totally agree. But there is a huge difference. For matchings, you actually have certificates in NP and CoNP, right? But so the interesting problem would be maximum stable set, right? So for example, you could have the following decision problem. Given a graph G, decide, so let's say you are given a certain stable set and a stable set S, decide whether G is a maximum stable set. Okay, this is one problem. And another problem which is related to matchings, but rather than looking at perfect matchings, I want to look at maximum matchings, which is a more general problem. Given a graph G and a matching M.
Excuse me, here decide whether S is a maximum stable set, right?
Yes, sorry, thanks. Decide whether S is a maximum stable set in G. right? So by maximum, I mean a stable set of maximum size. Thanks, Shanti. Okay. And here is another decision problem. Given a graph G and a matching M, decide whether M is a maximum matching in G. Okay, let's just give them names. So let's call this decision problem of maximum matching, which is related to perfect matchings. We'll talk about that in a few minutes. And this is a decision problem for maximum stable set. Okay, so they both look very similar, right? So again, a maximum matching is a matching that is of maximum cardinality among all the matchings, right? There is no cost on the edges. We are just looking at the size or the cardinality of each matching, which is the number of edges in it. So although these problems look very similar in definition, they are actually fundamentally different. The maximum matching problem, just like the perfect matching problem or most problems in matchings, is actually a polynomial time solvable problem. This problem belongs to P. In particular, it belongs to NP and CoNP. We are not talking about the certificates right now, but it is similar to Hall's theorem for bipartite graphs. And for general graphs, you need to do something slightly more sophisticated. However, this problem, on the other hand, clearly this problem is in one of NP and CoNP. Can someone tell me? Is it in NP or is it in CoNP? You want to decide whether a given set is a maximum stable set.
No, it should be in CoNP.
It is in CoNP, right? Because if it is not a maximum stable set, then there is another stable set which is bigger than this, and that is your certificate, right? Is that the reason?
Yes.
Exactly. So this belongs to CoNP. However, and we are not going to prove this right now, this does not belong to NP. Or at least, let me put it this way, not known to be in NP. That would be the correct way to put it. There is no easy way to convince someone that a given stable set is indeed a maximum stable set. There is no efficient certificate for this. And because it is not known to be in NP, it is also not known to be in P, right? That just follows by our discussion. They look very similar. Okay? Does that answer your question, Varun?
Yes, sir, it does. Actually,
Right.
now I understand this.
Right. So we are not going to prove this that it belongs to. It is, in fact, it is an NP. It is an NP hard problem. In fact, I think not the way I've stated it, but yeah, let me just say it as follows: computing a maximum stable set is NP hard. However, computing a maximum matching is actually a polynomial time solvable problem. Okay, and there is another way to relate these two. Maybe you can read about this later. Maybe I might even put it on your assignment. Let's see. So there is a concept called a line graph of a graph. I'll just tell you what it is without writing down the formal definition. So you are given a graph G, and you make a new graph. In this new graph, each edge of the original graph becomes a vertex. Okay, maybe you can do a small example. So let's say this is your graph G. It has 4 vertices and 5 edges, so that is going to be a bit interesting. E0, E1, E2, E3, E4. And what you do in this new graph, which is going to be called L of G, you put a vertex for each edge of the original graph. Okay, E0, E1, E2, E3, E4. Okay, and you make two vertices here adjacent if the corresponding edges share a vertex in the original graph, right? So E0, for example, will be adjacent to E1, E4, E2, and E3. Okay, E1 would be adjacent to E2, E0, and E4. E3 would be adjacent to E0, E2, and E4. And I think that is it. E2 and E4 should not be adjacent, and E1 and E3 should not be adjacent. Exactly. So that's your graph. And now can you tell me what does a stable set here? Let's see. Yeah, so a matching here, if you consider a matching here, what does that correspond to in this graph?
It should become the stable set.
Exactly. Matchings of G are precisely the stable sets of the line graph. That's a bit weird, right? Because we saw that one problem is efficiently solvable, the other is NP hard. So what's going on? Can someone explain what's going on here? Why does this seem counterintuitive? Unless you give it a deeper thought.
I mean, if you take the matchings of L of G, will that be a stable set?
That direction is not true. Matchings of L of G do not correspond to stable sets in the original graph. In fact, matchings of L of G, what are they? They are actually things like E2, E3, and E0, E4, right? If you look at those edges in the original graph, I mean, stable set requires a set of vertices, right?
Yeah.
Right?
Yes, so I think that is why, because it's only one direction. I think that is why we cannot show that it's solvable in.
Exactly.
Yeah.
Exactly. In fact, you can compute stable sets in line graphs of graphs because they are simply matchings in the original graph, right? But the problem is you want to solve the stable set problem in all graphs, not just line graphs of graphs. Does that make sense? Okay. All right. Varun, does that clarify your concerns?
Yes, sir, it does. It does
Right?
completely.
Okay. So there is a very strong connection. So when I teach the graph theory course, I give a similar example with Eulerian circuits and Hamiltonian cycles. That's another example of two problems that look very similar. If you don't know about it, you might want to read about it. But one of them, Eulerian circuits or Eulerian tours, is actually a polytime solvable problem, whereas the Hamiltonian cycle problem is a special case of the traveling salesman problem, which is NP hard. Okay, so I guess it's cool that the problems look very similar, but one is easy and one is not. Okay. All right. So are there any questions or concerns regarding all of this discussion so far? I want to turn to a new page after taking any questions. All right.
So I think like, do we get something interesting when we take, like, we have this graph at L of G. Suppose we take L of G,
Right.
like is that something of interest?
I don't know much about L of G. I guess you could ask interesting questions about L of G. So let's see. In that graph, your edges in this graph will become the vertices. So if you are going to look at this particular example, how many edges do you have? Four here. Let's just count the degrees, right? 4 plus 3, 7 plus 3, 10 plus 3, 13 plus 3, 16. So if you take L of G in this particular example, you would have 8 vertices. Is that right?
Yeah.
Okay. Um, yeah, I don't know if there is anything interesting about it, but it would be worth. I'm sure there is something in the literature on graph theory out there where people have considered this, but I'm not familiar with that material. Um, yeah, but I don't think algorithmically there would be anything very interesting. If there is something interesting, it is probably from a structural graph theory point of view.
So I think the only thing we can say is if G is a complete graph,
Hmm.
L of G, L of G, everything will be a complete graph.
If
That's the
G is a complete graph, L of G will be complete. I'm not too sure about that. You might want to think about it again.
okay.
Yeah, right. So that's a good thing to think about.
So
Uh,
I have a question.
yeah.
So the independent set is, we said it's in CoNP, but it is in NP, right? Because
Well,
the
the way I've phrased the decision problem, right, it is not
Mhm.
known to be an NP. Right. So the way you phrase it is very crucial. Right. So if you look at the computation problem, computing a maximum stable set, that is an NP hard problem. So, for example, if you want to convince someone that a given stable set is a maximum stable set, how would you convince the person?
Yeah, for this definition of for this
Right,
decision, yeah.
right. So, typically, it might be phrased in a different way. Decide whether it is not a maximum stable set, right? And then it becomes an NP and it's not in CoNP. So, the way you phrase it is very crucial.
Yeah,
Yeah, does that answer your question?
yeah.
Okay, good. Thanks. Yeah, so these titles I'm giving to decision problems are not standard titles. I'm just making them up as we go, depending on the problem. Okay, but in different books it might be phrased in a different way, and then the NP co-NP membership could change. Good. Okay, so the one nice exercise is G is a complete graph. Then is L of G also complete? Okay, so you can think about this offline. Prove it or find a counterexample. Okay, any other questions or concerns regarding all of this discussion? So in this course, we are going to mostly focus on problems that are polynomial time solvable. Right? In particular, our goal is to develop algorithms for combinatorial optimization problems um, using the theory of linear programming. Okay, but we can't just use the theory of linear programming. We might also have to use ideas from combinatorics and graph theory. Okay, but we are not going to see we are not going to see reductions to NP complete problems and stuff like that. That's not the focus of the course. Okay. So with that in mind, let's talk about matchings again. So what is a maximum matching? Uh, just for the sake of completeness, a matching M is maximum if the cardinality of the matching is maximum among all matchings of the given graph. Okay. So can someone give me a trivial upper bound on the size of a maximum matching? Supposing my graph is G, what is a trivial upper bound on the cardinality of any matching? Nothing fancy, very trivial.
Number of vertices by 2.
Exactly. Any matching has size maximum number of vertices divided by 2. Right? Does everybody agree with this? So what can you say about perfect matchings? So based on this observation, what can you say about perfect matchings of a graph, if a graph has perfect matchings?
So it will be a maximum matching.
Exactly. In fact, for if G has a perfect matching, then the perfect matchings of G are precisely the maximum matchings of G. Okay? Good. So one of the algorithms you'll be seeing in this course, as we have discussed before, is we want to find a minimum cost perfect matching in a graph. Right? So now your graph has costs on the edges. But well, if you want to find a minimum cost perfect matching, you also need to know how to find a perfect matching. Right? And that is what I want to talk about today a little bit. We are not going to see the algorithm in this module. We are going to see the algorithm in module 4 when we come to combinatorial optimization again. But I just want to talk about the main idea behind finding maximum matchings. Okay? Or let me just say, finding bigger matchings. So what I want you to think about is you have a graph G, you have a certain matching M, and your goal is to find a bigger matching if it exists. Right? That's the discussion I want to have today. So we are going to need some terminology. T is a graph, M is a matching. And you might have seen some of these terms in your previous courses. So let's take one example. Okay, so let's say I call this V0, V1, V2, V3, V4, V5. Okay, so let's say I consider this particular matching for the sake of discussion. Okay, so M is our red colored matching. So I just want to define some terms, but I'm not a huge fan of writing down formal definitions. So I'll just tell you by example. So V0 and V5, these vertices are not matched, right? In some sense, they are exposed in this matching. So we are going to call these M exposed, also known as M unsaturated vertices. I'm telling you both terms because I keep using both of them, so I don't want you to be confused. And the other four vertices, V1, V2, V3, and V4, these are M covered, also known as M saturated vertices. Right? They are saturated in the sense that you cannot include any other edges incident at those vertices, because if you do that, then you won't have a matching anymore. Right? Okay. Good. All right. Okay. So now I also want to tell you about paths, but we haven't talked about paths, so let me just make a small box here. So we have talked about cycles, right? Cycles look like this: C3, C4, and so on. Paths, you have probably seen them in your previous courses. They just look like cycle minus one edge. Okay? Or more visually, this is a path on 2 vertices, a path on 3 vertices. We'll generally talk about the number of edges. So I'm going to call this P1, P2, and P3. Okay? And the length of a path or the length of a cycle is the number of edges in that path or cycle. Length of a path or cycle is number of edges. Of course, in cycle, I could have very well said number of vertices because they are the same. But in the case of paths, we need to distinguish. Okay? Good. All right. And if a path has two ends, S and T, we might call it an ST path, where S and T are the two ends of the path. Okay? So I'm not going to write down formal definitions, but you get the idea. Technically speaking, a single vertex can also be regarded as a path, but let's not worry about it. We are going to mostly talk about paths that have at least one edge. Okay. All right. So, can someone give me a path in this graph using which I can get a bigger matching? So this matching M has two edges, right? Can someone give me a path so that using that particular path, I can get a bigger matching? You probably have seen this in your previous courses, so you can use that.
V0, V2, V1, V4, V3, V5.
Okay, let's write this down. V0, V2, V1. Right, there's another one there, okay. V4, V3, and V2. Is that what you said? Sorry,
V5.
V5.
Yes.
Yeah, good. So let's see, why are you suggesting this path? Let's put down the matching edges. The matching edges are V1, V2, and V3, V4. And if you look at these two vertices, the ends of the path, they are exposed vertices. Not only in this path, but in the graph itself. V0 has no red colored edges and V5 has no red colored edges. Right? So these are M exposed vertices in the graph G. And this is your path P. Okay, so can someone else tell me, why is this path good? What should I do to get a bigger matching?
I mean, the alternate edges you can take it as match.
Exactly. Let us throw away these edges and take the alternate ones. Okay, so instead of these two red colored edges, I'm going to put these three blue colored edges in my matching. So the matching could have had more edges somewhere else. That's not the point. I'm just focusing on this particular path, and I'm going to switch these two edges in the path, which are red colored, by the other three edges, which are blue colored. And the reason I can do that is because the two ends are M exposed, and the edges of the path, they alternate between not being in the matching and being in the matching. Right? So such a path, we are going to call it an M-augmenting path. And I'm going to write down formal definitions now. Okay? So this green colored path is an example of an M-augmenting path. Okay? And now I want to put down the formal definitions.
So like one doubt, like,
Yeah.
do we have to start at V0 and end at V5?
So you mean like V0 and V5, their order? Is that what you're referring to?
No, like I get that they should be included in the path, but do we have to start at V0 and end at V5? Is that important condition which you need?
You mean in this particular example? I'm not sure if I'm understanding your question.
No, like here in the path which we got, like we started at V0.
Yeah.
And we ended at V5, and we also have that V0 V5 are M exposed.
Right.
So are they like? Do we need that condition?
Right. So you tell me. So what did we do in this particular example? We switched the two red edges by the three blue edges. Supposing V0 was actually not exposed in the graph. Let's say there was another. Let me put it this way. Supposing my graph actually had another vertex here, and this edge was also in the matching. Could I still use the same idea? Can I now do the same switching idea and get a bigger matching, or does it not work anymore? So now my graph has 7 vertices. I already have a matching of size 3. So can I use the same idea? And this is a matching edge, V0, V6. Can I now use the same idea and switch on this path to get a bigger matching?
No, I think cannot be done.
Right? Because if I switch the two red edges to the three blue edges, now I will have two edges in my matching at the vertex V0. Both of these will be in my matching if I were to do the same operation. So I really need that these two vertices are exposed, because otherwise I won't be able to take these two edges, or at least one of them, in my new matching. Does that answer your question?
I think I'm a bit confused. I think I asked something else, but
Oh, okay. Okay. Sorry, I didn't understand. So I thought you were saying that what if this vertex is already matched in the graph? Can I still take it as the starting of my path? That's what I understood.
oh, okay.
Okay. Do you want to repeat your question?
Yeah. So I think what I asked, I got it now. So if you see this path, like we have V4, we went to V3, then we went to V5. Right?
Yeah.
So I was asking like, so instead of going to V3 from V4, if you go to V5 and end up at V3 at the end, so still
Right.
we get the augmenting path. Right?
Right. So then we won't be able to do the switching, right? We really want the edges to alternate so that we can switch these edges by the other edges. Does that make sense?
Yeah, right.
Right. So we really want to do the switching operation. And that requires us to have alternating edges in the path belong to the matching.
Right.
Right? Okay. Okay.
But then, like, if we have a zero matching, then choosing any path will work.
If we have a what matching? Sorry.
As zero matching.
By zero, you mean like empty set?
Yeah, empty set.
Right. So that will actually be covered in the definition. So you are talking about a case where you actually have two vertices. Both of them are M exposed. Is that right? And they are connected by an edge. Right. So if your graph has two vertices that are both exposed and they are connected and they connect to the rest of the graph in some way, you can always add this edge But you can also think of this as an alternating path, which is like a super short path. So I'll put down the definition, and you will see that this case is covered in that.
Yeah.
Okay. Okay, so let me just put down the definition, and I'll come back to this discussion that you are referring to. Okay. So let's go back to paths. So there are many different ways of viewing paths and cycles. One way of thinking of a path in a graph is it is a subgraph. Another way of thinking of it is it is a sequence of edges or a set of edges, right? But sometimes you may care for the specific sequence. So paths may be viewed as a sequence of edges, or for that matter, a sequence of vertices, because our graphs are simple, or a set of edges, or as a subgraph. Okay. So in particular, I want to take this viewpoint right now, sequence of edges. Okay. So G is your graph, M is your matching, I want to define an M alternating path. Okay. So maybe I'll just put down some drawings first and then write down the formal definition. So you could start with a non-matching edge, then you could have a matching edge. Okay, maybe I'll just put down some vertices first. Okay, so let's say some of these edges. Okay, and the remaining edges, I'm going to draw them red. Okay, so we have three different types of alternating paths here. One which starts with a non-matching edge, ends with a matching edge, or you can start and end with matching edges or with non-matching edges, right? The important point is that the alternate edges should be in the matching, and the other ones will not be in the matching because it is a matching. Okay, so a M alternating path is a sequence of edges E0, E1, E2 up to ER, such that for all I in 0 up to R minus 1, exactly one of EI and EI plus 1 belongs to the matching. Right? Or maybe let me just say it is a path with this sequence. So E0 is your starting edge and ER is your last edge. Okay, I think that is better. Okay, so that's what an M alternating path is. And what we had here in this example is an M alternating path with an additional property. That additional property is that the two ends of the path are exposed vertices with respect to that matching. Okay, so let me say an ST, an M alternating ST path. So S and T are the two ends of your path, is an M augmenting path if the two ends S and T are both M exposed in the graph G, right? In particular, M-augmenting paths, what will their length be? Can someone tell me? Can they be even length or do they have to be odd length?
They have to be odd.
It has to be odd.
Odd length, right? So observation is they must be odd length because you're starting and ending with non-matching edges in particular. M-augmenting paths are of odd length. By length, I am referring to number of edges. Okay. And the final observation I want to put down, and that will be the end for today's lecture, is that if I give you a graph G and a matching M, and let's say the graph has an M augmenting path. If G has an M augmenting path, then you can always get a bigger matching. What is the operation? Can someone tell me? What operation are we doing? We are throwing away the red colored edges and we are replacing it by the blue colored edges. Can you think of a set theoretic operation that does this?
Complement.
Not, it would be complement if this contained all the matching edges. But remember, your graph could be a big graph and this could just be a particular path somewhere in the graph.
Yeah, okay.
So it's not exactly complement, it's complement on this path. So there is another way to think about it, which is the
set difference.
Symmetric difference. Yeah. So what you do is you take the symmetric difference of this matching with the edges of this path, and that will give you a bigger matching. So this is going to be is also a matching, and the cardinality of this is going to be exactly one more than the previous matching you had, because what you'll be doing is you'll be replacing k edges by k plus 1 edges. Think about it. Okay, so maybe I'll put this as a do it yourself exercise. It's quite easy. Whenever there's an M-augmenting path, you just take the symmetric difference on that path. So the rest of the matching will remain as it is. On this path, you throw away the matching edges that were originally there, and you replace it by the edges that were not in your matching. And now you will have a matching which has one more edge than the previous one. Okay? And this is the main idea that is used for finding maximum matchings. We'll continue on Wednesday and complete this discussion. All right, so that is the end for now. Are there any questions?
So the M alternating path, it does not need to have all the edges in the matching, does it?
Right, it does not need to. I took a small example, therefore it had it. So let's do another example. So supposing this was my same graph. Okay, and let's say the matching was just one edge. Okay, and let me call the vertices v0, v1, v2 the same way. Supposing this is my matching in the graph. So now can you give me an M-augmenting path? Okay, but this is not what you're looking for. You want an example where not all the edges of the matching are included. Okay, sorry. Sure. So let me make a slightly bigger example. Let's consider this graph. Okay, and let me call the matching edges as this one and this one. Okay, and let's label the vertices as 0, 1, 2, 3, 4, 5, 6, 7. So now can you give me an M-augmenting path that does not contain all the edges of the matching?
5, 1, 2, 6.
5 to 1 to 2 to 6.
Yeah.
Is that really an M-augmenting path? I want you to think about it again. 5 to 1 to 2 to 6. There is one
I'm
problem
sorry.
here.
0, 1, 2, 3.
Exactly. 0, 1, 2, 3. Great. So let's look at 0, 1, 2, 3. And here the only edge in the matching is 1, 2, and 0 and 3 are exposed vertices. So let me circle them by a red color. Right? So now you can get a bigger matching by replacing 1, 2 by this edge and this edge, and you will continue keeping the original edge. That will not change. So now you have a matching of size 3 in the green color. Does it answer your question?
Sir, just could you repeat that last statement? I think I got missed something. I could not understand what you just said. The green part thing I just could not understand. Could you just repeat that?
Right. So I'm just showing this operation. So we had a red colored matching, and what I'm doing is I'm taking the symmetric difference of the red colored matching with the edges of this path. What is the path? It's this path. So when you do that, you get the green colored matching that I've shown. Right? So if your red colored matching is 1, 2, and 4, 5, your path P, what are the edges? 0, 1, 1, 2, and 2, 3. Can you tell me the symmetric difference of these two sets? I'm using this for symmetric difference. So what's the symmetric difference of these two sets?
0, 1, 2, 3, 4, 5.
0, 1, 2, 3, and 4, 5. Great. And that is exactly the edges I have shown here in green color. Right? So we went from a matching of size 2 to a matching of size 3. Do you agree? Are you there?
Yes, sir. I understood what you were saying.
Right? Right. Okay. All right. Any other questions or concerns? So the lecture is officially over, but I'm still here for another 5 minutes or so, if there are any questions or concerns.
Hello, sir.
Yeah, go ahead.
So, finding an augmenting path does not guarantee that we will get a matching of maximum size. Is that true, sir?
Good point. So you agree that if we find an augmenting path, we will get a bigger matching, right?
Yes, sir.
Right. Okay. So this is exactly what I wanted to discuss in the next lecture. So it turns out this is it. Almost every algorithm that finds a maximum matching, this is how it proceeds. It will find an augmenting path and get a bigger matching. The fact that whenever your matching is not maximum, there must exist an augmenting path is something that you need to prove, and you might be proving that in your first assignment.
Okay, sir.
Right? So basically the whole game is finding augmenting path. If you can do this in polynomial time, then you will be able to find a maximum matching in polynomial time. Does that answer your question?
Yes.
Right. Okay, nice.
So just a extension of what you were just saying. So you are talking about augmenting paths. The other place I've heard augmenting paths is in Ford-Fulkerson algorithm. So is
Right.
it the same augmenting path or is it different? So there also we talk about ST path where S is the source and T is the sink.
Right. It's similar. It is the reason the term is the same is because bipartite matchings in particular. So what is the reason of using augmenting? So augment just means to increase something, right?
Yes, yes,
You are able to make something bigger by
yes.
augmenting, right? That's the idea. So
Hmm.
this term augmenting path, you see it in different contexts in combinatorial optimization.
Okay,
And sometimes there are direct translations between them. So
okay.
in particular, bipartite matchings can be solved using flows.
Huh.
And if you do that, then these augmenting paths will, if I'm not mistaken, become exactly those augmenting paths in the flow theory that you are doing.
Yes, yes. So that is true. The last part is clear for me. Okay.
Right. Interestingly, non-bipartite matchings cannot be solved using max flow min cut. And so
Non.
the augmenting path notion in matchings is actually necessary. You can't just do it by flows for non-bipartite graphs. At least
Okay.
it is not known to be doable, to
Okay.
be more precise. Yeah.
Okay.
Okay.
I mean, I
So yeah.
just got that relation between because I've heard that term a lot, and then here also
Yes.
I'm hearing that.
Yes. So it's not a total coincidence. Some of
Okay.
these things were developed by the same group of people, and they came up with similar terminology.
Okay. Thank you, sir.
Sir?
Yeah. Go ahead.
Yeah. Sir, actually, this is the means matching of largest cardinality because it's 3 and there are 6 vertices. So 6 by 2, 3. So we can say we have
Mhm.
got the
Right.
uh,
In which graph are you looking at? The 8 vertex graph or the previous one?
uh, the
This one.
6 1, 6 1.
This one, right?
Yes,
Yes.
yes.
Yes, you're right. So in this particular example, by doing this one augmentation, we will get a perfect matching. In particular, it is a maximum matching.
Yeah, so means we are sure that we have got the matching of largest cardinality.
Yes, in this example, it's easy because it's a perfect matching. So it has to be a maximum matching. However, if your graph had more vertices, then you would need some argument to convince that this is actually a maximum matching.
Yeah, maybe means I'm telling that suppose I have a graph of 10 vertices
Okay?
and I have got a matching having 5 cardinality 5. So I am sure
Okay.
that I have
Then you
got
are
the
done.
perfect matching. Yeah.
That's right. That's right. That
Okay.
is because of the observation we had here.
Yes, yes.
Yeah.
Okay, sir.
Yeah. Good. Thanks.
So, is there any name to this algorithm? I just want to Google and read more about it or something.
Um, so, I mean, you can search for Edmond's algorithm, which
Is
is
it
for
the
non-bipartite graphs.
Edmund Karp? Is that the same?
Edmond Karp, if I'm not mistaken, is a faster way to do max flow min cut.
Max flow min cut.
But just Edmond's algorithm, or called the Blossom algorithm,
Okay.
generally refers to finding a maximum matching in
Okay.
any arbitrary graph, not just bipartite.
Okay.
Right?
I will
But this
look that.
particular idea that you just have to find augmenting paths in order to get a maximum matching, that is due to Berge from the 1950s, I think.
Okay. I'll
Okay,
just look this up
so you
because
can
I
search
did
for
not.
Berge's theorem.
Okay, Berge's theorem. I'll
Yeah,
look that up.
yeah, and we'll talk about the theorem in the next lecture as well.
Okay. I just wanted a name so that I can Google it. I mean, Googling this will be difficult.
Sure, sure, I get it. Yeah.
Thank you, sir.
Okay, you're welcome. So I'll stop recording, but I'm still here for any other questions or concerns. I just don't want the lecture to become too long.